Okay, this should be a pretty brief video just to show some computations with permutations. Here we have 1264 to the third power. Now, one way to represent this is as a cycle. 1, 2, 6, 4. Right. And 1 goes to 2, 2 goes to 6, 6 goes to 4, 4 goes to 1. All right, now, if I'm going to cube it, then basically I'm going to do the permutation 3 times. I'm going to apply the arrows 3 times. So I just follow 3 arrows. Right? So I have, starting with 1, 1 will go to what? 1, 2, 3. It goes to 4. And in keeping with the way we do cycles, let's start now with 4. 4 goes 1, 2 to 6. 6 goes here, here, here to 2. And 2 goes here, 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 back to 1. We close it, and there's our answer. Now you could also do the same thing, writing the permutation 3 times. 1, 2, 6, 4, 1, 2, 6, 4, 1, 2, 6, 4. And follow along our usual permutation rules. Start with 1. Here it says 1 goes to 2, 2 goes to 6, 6 goes to 4. What we're actually doing is following these arrows. All right, so we still get the same answer. Then start with 4. 4 goes to 1, 1 goes to 2, 2 goes to 6, etc. And we get the same answer. Now, if I do it to the 4th power, an easy way to do that is just take the 3rd power and then multiply it once again by 1264. So that's one way to do it. You could start all over again, but why reinvent the wheel, you know? So let me just clarify this. This is 1264 cubed is equal to this. So 1264 to the 4th power would just be equal to 1264 times 1264 to the 3rd power. Why not? And I know what 1264 to the 3rd power is. 1264 times 1462. Okay, so let's see what happens. Remember, when we do permutations, go right to left. Let's start with a 1. 1 goes to 4 here. 4 goes to 1. Okay, so 1 stays fixed. We don't even need to write it. I'll just write it just to show that we've done with it. All right, so what's the next element that we haven't looked at? Let's look at 2. 2 goes to 1. 1 goes to 2. What do you know? All right, let's see where the next element is 4. 4 goes to 6. 6 goes to 4. What do you know? Next element is 6. 6 goes to 2. 2 goes to 6. And we have 6. Okay, this is the ID. Okay, so 1264 to the 4th power is ID. Right. So you don't need to hand this one in, write it up, but you have a similar problem with a different permutation. I just wanted to show you kind of how you can approach that. The other exercise I'm going to do in this section is computing these values. The order, this absolute value sign, these vertical bars, means order. So you're not computing just a permutation, you're computing the order. The order is a number. And the order of a permutation is the smallest integer, or smallest positive integers that makes the permutation back to the identity. We just saw that 1264 to the 4th power is equal to the identity. So the order of 1264, we write that as the order of 1264 is equal to 4. All right. It's the smallest positive number that takes you back to the identity. Okay. So for instance, the order of the identity is 1 because identity to the 1 is 1. But identity is the only permutation that has order 1. This one has order 4. Now notice this is a cycle of length 4 and it has order 4. That's not a coincidence. You'll see that in many patterns and other examples that you have. Right? So here we have the order of 1254 squared. Now you might be tempted to say, well, 1254 is a cycle of order 4, is a cycle of length 4, so the order is 4, but you need to be careful. We have to compute this permutation first and express it in terms of cycles. So the order of 1, 2, 5, 4 squared, I have to compute 1, 2, 5, 4 squared. Now, you could write 1, 2, 5, 4, 1, 2, 5, 4, but why do that? Let's just follow along like we did before. What does 1 go to? Well, 1 goes to 2 and then to 5, so 1 is going to go to 5. What does 5 go to? 5 goes to 4 and then to 1, because you're squaring it. So you here have, so 1 goes to 5 and 5 goes to 1. We've closed off that cycle. That's a transposition or 2 cycle. Well, now what's the next element we haven't looked at? It's 2. 2 goes to 5 goes to 4. And 4 goes to 1 goes to 2. So we close that off. So now we've looked at everything, 1, 5, 2, and 4. You can verify 4 goes to 1 goes to 2. Yes, we did that. Okay. So we have the order of this. Now what's the order of this? Well, if I take 1, 5, 2, 4, and I square it, now these are disjoint cycles. So really, they act independently. It talks about that in the chapter. So I can write this as 1, 5 squared times 2, 4 squared. And I can only do this because the cycles are disjoint. That's the only reason I can do this. Now what's 1, 5 squared? Well, it's a transposition. You're doing it twice. It's just like in symmetries we had flips. This is like a flip. So that's going to be the ID times the, and the 2, 4 squared is also going to be the ID. So that's equal to ID. All right, so we have that this permutation squared is the identity. So that means that the order of 1, 2, 5, 4 squared is equal to 2, since 1, 2, 5, 4 squared is equal to the identity. All right. So let's look at a more complicated example in part B. And you have to take all this stuff together. Okay. So let's see. So for part B, I'm going to have to actually figure out that permutation. So let's go to it. No sense wasting time. All right, so here's order of 1, 3, 6, 5, 8 squared, 4, 7, 3 squared, 1, 2, 5. Now the first thing to look at when you have an expression like this is, are the cycles disjoint? And unfortunately they're not. So they're not disjoint, so I'm going to have to compute this all out by the entire product. So let's just get to it. Starting with 1, this permutation takes 1 to 2. Then 2 under this permutation doesn't do anything because there's no 2 in there. Under this permutation also doesn't do anything. So 1 goes to 2. All right, let's see what 2 goes to. 2 goes to 5. 5 under this permutation doesn't do anything. 5 under this permutation goes to 8, but I've squared it, so it goes 5 goes to 8 goes to 1. So that says goes 1 back. That goes back to 1. I have a transposition, close it off. Now remember, when you follow something through, you have to follow through all the way to the end, right? 2 goes to 5. I like to think of this as a coat room. 2 changes into 5. And when he goes into this coat room, he doesn't change coats. When he goes into this coat room, he actually has to change coats twice, so he goes to 8 and goes to 1. So 2 goes to 1. Follow all the way through. Now don't stop in the middle, follow all the way through. The important thing is, what does 2 end up when it goes out the other side? So it goes back to 1, and 1 went to 2. We have a transposition. We close it off. Let's go on to the next one. How about 3? Well, when 3 goes into this coat room, he doesn't change coats. Here he's got to change coats twice. So 3 goes to 4, goes to 7. Then he goes to this coat room. He doesn't change coats again. So 3 goes to 7. All right, so let's see where 7 goes to. 7 goes into this coat room. He doesn't change coats. 7 now changes coats twice. He goes to 3 and then to 4. Okay, and then once he's got 4, he doesn't change coats here at all. So here he gets 7 goes to 4. All right, what about 4? 4 goes into this coat room, doesn't change coats. Here he has to change coats twice again. 4 goes to 7, goes to 3. Then 3 changes coats twice here. 3 goes to 6, goes to 5. All right, so 4 goes to 5. What about 5? 5 changes codes here to 1, goes to this coat room, doesn't change. Then here has to change twice. 1 goes to 3, goes to 6. Okay. What about 6? 6 goes into this coat room, doesn't change. 6 goes into this coat room, doesn't change. 6 goes into this coat room, 6 goes to 5, goes to 8. Okay. What about 8? 8 goes into this coat room, doesn't do anything here, goes in here. 8 changes codes twice. 8 goes to 1, goes to 3. 8's back to 3. Close off the cycle. We've taken care of 1, 2, 3, 4, 5, 6, 7, 8. That's the entire cycle. All right, now, we want the order of this, and these cycles are disjoint. Okay, so that means we can square them independently. So let me call this permutation. Let me just call it sigma, because that's a nice name for a permutation. So what about sigma squared? Well, it's going to be 1, 2 squared, 3, 7, 4, 5, 6, 8 squared. I can square them independently because they're disjoint. All right. Now, is that the identity? And the answer is no. Because if you square this, you can see that although if you square 1, 2, you get the identity. If you square this one, 3 goes to 4, it's not the identity. What about sigma cubed? Okay, I don't even need to write this. This one is not the identity, right? That's 1, 2, so that's not the identity. Okay, so we can see right away that sigma to any odd power is not the identity, because this 1, 2 to any odd power is not going to give me the identity. So sigma to the odd is not the identity. All right, so let's go on and see what else we can do. All right, how about sigma to the 4th? Okay. Sigma to the 4th is 1, 2 to the 4th times 3, 7, 4, 5, 6, 8 to the 4th. Now, what about this permutation to the 4th power? Well, just look at 3. 3 goes to 7, 4, 5, 6. So this has 3 goes to 6. So that's not the identity. I don't need to compute anything else. I already know it's not the identity. Let's go on. Now I know sigma to the 5 doesn't work, so let's try sigma to the 6th. Sigma to the 6th is 1, 2 to the 6th. And then we have 3, 7, 4, 5, 6, 8 to the 6th power. Now we're getting somewhere. This 1, 2 to the 6th is identity. Now what about this other one? Well, I have to apply the permutation 6 times. So if I start with 3, 3 goes 1, 2, 3, 4, 5, back to 3. Very good. How about 4? 4 goes 1, 2, 3, 4, 5, 6. Now this is a 6 cycle, so the order in fact is 6. So this is both identity, so that's equal to the identity. So that means that the order of sigma is equal to 6. So that's a sigma. It looks like the order of 6 is equal to 6. That's why I've been kind of making the sigma a little bit like that. The order of sigma is equal to 6. Okay, so that finishes that. All right, so hopefully that gives you some idea how to do these problems quickly. The idea of having these problems is just to get your practice up working with permutations in cycle notation. You need to be very quick and confident in that kind of computation. All right, that's it.